Question number 31. How many significant figures should be present in the answer of the following calculation? So we need not calculate, we just need to figure out the number of significant figures. Now for addition, first let's go with multiplication and division. That's the first two. So for multiplication and division, our answer should have the number of significant figures should be equal to the least number of significant figures which are present. So instead of telling you, okay fine, I'll just show you this. So this number has 1, 2, 3, 4. 4 significant figures. This number on the other hand is 1, 2, 3, 4, 5 significant figures. This has just 3 significant figures and this has 4 significant figures. Now from all of these, the number of significant figures of the solution should be equal to that of the least number of significant figures that are present. So because of that, we will the number of significant figures of this solution would be 3 significant figures. Okay, so now think about this one. The next problem, 5 into 5.364, right? So based on what you see immediately, the first thing we will end up writing is one significant figure. But this is wrong. I'll tell you why. Now when I have a whole number, now had this been 5.0, then we can say it has a certain number of significant figures. But it is 5, which means it has an infinite number of significant figures, because no matter how many zeros I put, the value is going to stay 5 first of all. But because we put 5, we have a question as 5, we will not be considering this because it has an infinite number of significant figures. So in that case, this digit has just 4 significant figures. So the number of significant figures in this is equal to 4. Right? So because this is a whole number and a whole number can have an infinite number of significant figures. Had it been 5.0, it means it would have 2 significant figures. But it is 5 and 5 can have any number of significant figures. Thereby this particular answer should have 4 significant figures. Now the last one, here you have addition taking place. So in this case it has to do with the decimal point. Okay, so let's first calculate 0.0125 plus 0.7864 plus 0.0215. And when this is all added, it has 0.8204 as the answer. And according to addition for scientific notation, the number of significant figures, here we will consider the number of digits after the decimal point. If suppose I had one of these digits, all of them have 4 digits after the decimal point. If I had only 3, then we would have had only 0.82, or rather the first 3 digits would have only been written in the solution and the number of significant figures would have been 3. But because you have 4, so the number of significant figures are 4 significant figures. To understand the concept of significant figures and to understand how to do various calculations using significant figures, do check out the video about the same, and I am sure that will provide you a deeper understanding into this particular topic. Question number 32. Use the given data in the table to calculate the molar mass of naturally occurring argon isotopes. So we've been given the isotope and we've been given the isotopic molar mass and the abundance. So first of all, let's take this. So there was a detailed explanation about this that we did, and we took the example of carbon isotopes and we'd done the same problem. So there we calculated the mass of 100 atoms first and then divided it to find out the mass of just one atom. So instead we are going to be doing just one step. So average atomic mass of argon will be equal to the isotopic molar mass into the abundance. So 35.96755 into 0.337 plus 37.96272 into 0.63 in plus 39.9624 into 99.600 whole divided by 100. So the reason I'm putting divided by 100 is because we are, when we do it alone, when we just take the numerator, we are calculating the atomic mass of 100 atoms of that particular element. So in this case it's argon. So if we did not put divide by 100, it meant it's for 100 atoms. But because we are putting it as divided by 100, the atomic mass of that particular element is getting calculated. So when this is simplified, we get 39.948 grams per mole. Right? So average atomic mass is calculated by merely multiplying the isotopic mass into the abundance and adding all of the individual values up, dividing it by 100. For a detailed explanation of the atomic mass and calculation of the average atomic mass, do check out the video I done on molar mass and atomic mass. Sorry, molecular mass and atomic mass. Question number 33. So we need to calculate the number of atoms in each of these. First is 52 moles of argon, second is 52 U, that is AMU or atomic mass unit of helium, and 52 grams of helium. Let's start. So the first one, 52 moles of AR or argon. So 1 mole of argon will have 6.022 into 10 to the power 23 atoms. So 52 moles of AR will have how much? That is equal to 6.022 into 10 to the power 23 into 52 atoms. So when this is simplified, we get the answer as 3.13 into 10 to the power 25 atoms. So we just use the basic relation of the number of atoms to the Avogadro's number, the number of moles. 1 mole has 6.022 into 10 to the power 23 atoms. So 52 moles will have how much? Second one is 52 atomic mass units of helium. So 52 atomic mass units of helium. So atomic mass of helium is 4. So 4U of helium will have 1 atom. Then 52U of helium, that is the atomic mass unit, will have 1 by 4 into 52 atoms. We are just cross multiplying and this gives us 13 atoms. In the third one, we are taking 52 grams of helium. So 4 grams of helium. Here we are taken the atomic mass in atomic mass units. Here we are taking the gram atomic mass. So gram atomic, 4 grams of helium has 6.022 into 10 to the power 23 atoms. So 52 grams of helium will have how much? So this is also cross multiplication. So 6.022 into 10 to the power 23 divided by 4 into 52. atoms. Here, because for the units of gram is getting cancelled and leaving behind the atoms, number of atoms. So this, when simplified, gives us 7.83 into 10 to the power 24 atoms. So this particular question is quite unique. The reason being, it shows us the various relationships between the number of moles and the number of atoms. So generally 1 mole of any substance will have 6.022 into 10 to the power 23 atoms. So even if we are taken 52 moles of any element, it could be helium, neon, argon, any element, that would have 3.13 into 10 to the power 25 atoms. So this is very general, but these two answers are very specific, because here we've considered the fact that the atomic mass unit of helium is 4U. So 4U will have just one atom, then 52U will have how much? Similarly, 4 grams is having 6.022 into 10 to the power 23 atoms. Here we've considered the gram atomic mass, and then we're comparing it with 52 grams of helium. So these two are pretty specific for helium, whereas this, on the other hand, is pretty general. Even if I had taken 52 moles of potassium, calcium, any element, the number of moles would be 3.13 into 10 to the power 25 atoms.